So what I want to show you today are two papers. Here. All right. Okay. So the first is the ICCV 2025, and the second is the CPR 2026. Okay, and okay, fine. They are highly related, but totally different. But I will explain why. Okay. So first, I need to explain what is temporal action detection. It is very intuitive. It's just given a video, we want to recognize or detect where is an action and which frame is it the starting frame and which frame is the end frame and what of the class of the action is. So first, okay. But however, this is under hot topic. Very few papers are addressing this problem. So you can see there's no paper addressing this topic in WACV, and there's only one paper addressing this problem in ICCV 2025. Okay. And why I am interested in this topic? Because the second paper, Ken and I are co-authors for the second paper. So we will go to Chih-Yuan this year to present this paper, and those I won't be able to be here, so I will find a substitute teachers for you for this case on that week. Also, let me explain. So our paper is a findings track paper. So what is a findings track? Okay, it is the new track in CPR 2026. CPR never ran this track before, but however, it is traditional for the natural language processing community. For example, the NLP, they have the finding track for many years. And beginning from ICCV 2025, they also set up the workshop, findings workshop, to accept this. So this is a keyword. They are technically rigorous, but not sufficient novelty. Okay. So, and the new tracking is useful because many authors, when they got rejected from a top conference, they will try to revise their paper and submit it to the next top conference. So it will use a lot of reviewers to review the same paper. Okay, so to avoid the waste of the reviewers' time and effort, they created the finding tracks to accept the papers. The quality is okay, but the novelty is not so high. So our paper was accepted by the finding track. Okay, so let me tell some details. In ICCV, because the finding track is a workshop, so authors need to submit their papers to the workshop. But in CPR, this is not a workshop. It is directly managed by the CPR program chairs. So they will ask area chair. Do you know what is a program chair and what is area chairs? Okay, let me explain. So suppose, assume this is a pyramid. Okay, the top is one is the program chair, and he will collaborate with his other program chairs. They manage everything. So there may be some, for example, agenda program chair, general program chair, publication program chair. They just like the CEO, CFO, or CTO in your company. Okay, but however, who will be in charge to review papers? Reviewers, right? They will hire a lot of reviewers or invite a lot of reviewers. Who will manage those reviewers? That is the duty of area chairs. Okay, so area, for example, I am area chairs for ICNO and ECCV. So I will have a pile of, say, 20 papers. And every paper will have at least 3 reviewers. So I will collect at least 60 reviews from many reviewers. If they forgot to submit a review, I will send emails to notify them, oh, your review is due. Please give me your review quickly. Okay. Then, for every paper, I will have at least 3 reviews, and the review will have their recommendation, rejected or accepted. So some of them are very clear, highly recommended, because all 3 reviewers recommend accept. So the paper almost definitely will be accepted. And some papers, the quality is very low, the format is wrong, or the references are incorrect. They will receive very bad or low scores for their papers. So this kind of paper will definitely be rejected. But however, some papers are around the boundary. 2 reviewers suggest accepted, but 1 reviewer suggested rejected. Then that is our area chair's duty to check whether the paper is good enough to be accepted, or we should recommend to reject this paper. We need to read the paper and read those reviews and encourage authors and reviewers to raise and answer those questions. And finally, we will recommend our own review or recommendation. That is the meta review. Okay, to what? To the senior area chair, and the senior area chair will recommend their decision to the program chair, and then the conference will release the final decision whether a paper is accepted or not. Okay, so this is a hierarchy. Okay, there are only maybe 10 area chairs, and there are maybe 100 there are maybe 10 program chairs and 100 senior area chairs, and maybe several hundred or around 1,000 area chairs, and there are a lot of several thousand reviewers. Okay, so this is the hierarchy. Okay, so in CVR 2026, the paper can only be accepted by the finding tracks by the recommendation of area chairs. So it means the authors cannot submit their paper to the finding chairs. Only area chairs think, okay, this paper is good, technically sound, but normatively insufficient. Then they will recommend the paper to their senior area chairs to accept. And our paper belongs to this category. So they will release the acceptance of finding tracks before the deadline of general workshops. So and this is the opt-in mechanic. It means if we decide, okay, the paper will be published in the finding tracks, we cannot publish or submit to any following conferences because it will be treated as published already. Okay. So some people or some authors, they may think, oh, our paper is hybrid. We don't accept the second tier publication. So they can refuse to be accepted and try to implement their new algorithm or etc. and submit to the next top conferences. Okay. So this is the title of our paper, TP square deter, right? And I will show you why. Okay. The idea is there is an existing algorithm called GAP. It tries to modify the GAP to improve the performance. And then, okay, I will show you how to do it. They will add a new feature pyramid on top of the input extracted features. And they will add a deeper supervision and early supervision. I will show you some figures later. All right, okay. And Okay, so I will show you two papers, right? And there are two different tasks. The first is action. Sorry, here's wrong. This is action detection, not recognition. Action detection, temporal action detection, and the second is temporal action proposal generation. So what's the difference? So suppose there is a video clip, and there are several actions within the clip, and then for temporal action detection, they want to answer the question, what the action is or what the class is. But for temporal action proposal generation, they don't care about what the action is. They only care about the beginning and the ending of this action. So for temporal action proposal generation, they don't need the class label. Okay, so let me show you an example first. So this is a video from the ActivityNet dataset. And here, okay, so let's take a label first. So here you can see it is belong to the training subset and the resolution, and it's the YouTube URL. And the most important is the annotation. First, you know the class. The class from here, the class is a layup drill in basketball. Okay? And you know the beginning and the end time of this class. So let's take a look of this video. Pay attention to the 20-second beginning time.
Rondo fake pass moves. When you're dribbling the ball, you pick it up there, you fake the pass behind your back, and then you finish it. You can lay it up, you can pass it, whatever you want to do. So you get the dribble, you pick it up with that one hand, fake that pass, look off, head fake is an important part of the.
Okay, so this is the beginning time, 23 seconds. And then
fake. And then you go ahead and do what you want to do with the ball, whether it be pass, shoot, whatever. So here, I want to try to get a better grip off the dribble. There's a place, like I have it there, if you can't dip it for a while. You can also go completely around your back. Just make sure you get that head.
Then, okay.
To see a vertical, go to DreAllDay.com/jump. Get the jump manual. When you get it, I'm going to give you 5 free hoop handbooks.
Let's start here. Because it is 1 minute and 40 seconds. So it is the end of the action. So why do I want to show you here? Do you think the label is accurate or not? Totally inaccurate, right? That's right. That's the problem of the ActivityNet dataset. That label is highly annoying.
Any free DVD, all you got.
What?
It's horrible.
Yeah, very horrible. Terrible, horrible. Okay.
It's not even like, okay.
Oh, is it okay? Okay, fine. So let me explain. So here, this is a paper published in ICCV 2009. Okay, so 9 years ago. So from the net BMN. So this is a boundary matching network for temporal action proposal generation. So here you can see the keyword. The keyword is action proposal generation. So do they care about the class label? No, that's right. Totally correct. They don't care about the class label. What they care about is the start and end time. So the idea is straightforward. They developed a network. So the network is the boundary matching network. What is the output? The probability of the boundary. So this example, suppose this is a ground truth start. So their network should generate a peak around the start time here, and generate a peak for the end of the time. Okay. So suppose this is their generated result. So they will assume from the generated probability distribution, there should be a beginning time and there should be an end time. So between the beginning and this end, okay, there should be an action here. They don't care about what the action is. They just want to know, okay, there should be an action. And here, this is another start and end time. So from here, this is their first step. Why do they want to do it? First, they assume they can detect where the action or actionist is. Then they will do another, they will crop the clip and analyze the clip using a very straightforward classification algorithm to do it. So this is a two-stage solution. First, detect the beginning and the time, and then only focus on this clip to analyze what the class would be. Okay. So you can see, I should say, I give you an example. The activity 1.3 dataset is very, very noisy, right? And I will show you another example. So this is also from activity 1.3. So this is the pole vault. Pole vault is use a pole to jump very high. That is a type of action. Again, pay attention to the segmentation annotation. For the 3.5 second and the end at 42 seconds. So let's take a look. Okay, so this is the beginning of the action. Okay. And then go. So yeah, of course, this is a. Okay, it's okay, right? So let's go to the 42 second. 42. Yeah, it's almost here. Okay, the set. What I want to show you is the data set from my perspective is highly inaccurate. Okay, but however, you can see there's another problem. Suppose you have a label pole vault. Then how do you label what is the beginning and the end of this action?
I think that's the issue, right? Because you're saying you don't have classes, but you're implicitly defining classes when you define the training data. Like you said, right? Like pole vaulting might be just the jumping over bit, it might be the running.
That's right.
You have to define the class in some way.
That's right. So then I should say, if we use this data set, activity pointer, activity net 1.3, do you agree or do you disagree with this annotation?
I personally disagree with it.
Yeah, okay. Both you 1, 2, 3, at least the three of you don't disagree with this annotation. But however, this is the benchmark used for this study. Okay. But no one discussed this problem. This is the quality of the data set. All right. All right. Okay. So let me show you. Okay. So for the previous two data set, we have only single segment, right? Here I want to show you. So this is another instance in the activity point 1. So there are multiple segments, and I want you see how accurate or inaccurate they are. So let's take a look. So this from here you can say this is also pole vault. Okay, so let's. Oh, so let me explain first. So this is the raw data. Okay, and if it belongs to a segment, I will show the segment in this large region. Okay, so that you can easily sense which is the beginning of the segment, which is the end of the segment. Let's go. Oh, okay. So what happens? Sorry. What happens? Okay, I want to show you is here. So when you see the large screen, it means it is a segment. And let's go on. Yes. So what I want to show you is I hold down here. Yes. Every time I click the button. Okay. So what I want to show you is when you see the screen become black, it means this is the end of a segment. So here I want to click the left button. Let's go through the video. What? Sorry. What should I cannot? Oh, this is the end. Well, fine, let's stop it. So what I want to show is, do you think the label is accurate or not? From my perspective, the label is very, very bad or poor. Okay, but however, this is the ActivityNet 1.3, and you will see the dataset in the following slides. Let's go. Okay, so there's another problem. Because ActivityNet only provides the labels, and many YouTube links are no longer valid. So the owner can stop sharing the videos. Or YouTube will remove that. Okay, let's see another. So that is ActivityNet 1.3. And then another widely used dataset for the temporal action detection is the TUMOS 14. Okay. The TUMOS 14 is also okay. It is also the collection of YouTube, but there are some differences between first. For temporal action detection, there are only 20 classes. I should say, TUMOS 14 is a large data set. There are two tasks. One is the action recognition, just to classify them. And the second is the temporal action detection. Okay. So for the temporal action detection, there are only 20 classes. So this is the 20 classes of the temporal action detection. Okay. And you can see all of them are sports. That's right. Because the training set here is the UCF 101. Okay, the UCF is the University of Central California. And the 101 means 101 sports actions. Because this is TUMOS 14 is derived from the UCF 101 dataset. So all of their classes are sports classes. But however, in ActivityNet 1.3, there are more daily actions. So let me show you. So now we can still get the annotation from the TUMOS 14 dataset, but there's a problem. I cannot download its videos. The official website is still running, but all of their links for videos fails. I cannot download. And I asked Gemini and ChatGPT, where can I download the dataset? And they told me there is a community maintained mirror of the dataset. But however, I cannot find it. And they also suggest me there is a P2P, peer-to-peer seed which can download the dataset. Yes, I found the seed, but when I try to download the dataset from the seed, they told me there are no active sharing users. So that I put my seed, I run the download program using the seed for 0 days, and my progress is still 0. So there's a problem where, okay, so that's a problem. Currently, the 2 datasets, tumors 14 and activity point 1.3 from my staff are invalid. I cannot get that. I cannot do experimental on that. Okay. But however, our paper still report numbers on the 2 datasets. So don't you feel it's very weird? You cannot get a dataset, but why can't you do experiments on that? Okay, so let me tell you the reason. So as I mentioned, our paper is a modification based on gap. So this is the gap. And the authors of gap, they provide a pre-extracted dataset using clip video encoder on the 2 datasets. And they generate the files. For activity net 1.3, only 13 giga, and for tumors 14, only 1.28 giga. So it is very easy to download that. Although we cannot get the raw videos, so that we can still do experiments on the. But there is also. So let me show you what it looks like. When we download the dataset, so here you will see there is a clip feature 8 frame. So what does it mean 8 frame? The 8 frames, because for every video, a video composes of several frames, right? But they use 8 consecutive frames to extract 8 video, 8 clip text image encoded features. Every frame will have a feature, and then they concatenate 8 features. They call it the snippet. So here, for every video, for example, this is the tumors 14. There are test set, validation set, and training set. Then, for the test set for video, for this video number, they extract those features and save it as the NumPy array. So that we can access those files directly. However, here you can see, I want to explain what is the problem we encounter right now. Because we cannot access the raw video. So if I want to try to apply, so clip is image. We have a clip image encoder, but can we use other image encoder? For example, Dino V3. Dino V3 in general is more powerful than clip. But can we apply Dino V3 to extract the more powerful representations? No. So that's the problem. And because we don't have the raw videos, we cannot observe what happens, or is the label is correct or not for the raw video. So that's the reason why I show you for the 3 example videos, the annotation is highly inaccurate. If we have the raw video, we can measure, where do we need to update those labels, or do we need to ignore those labels? But no, here we cannot. We only have the clip pre-extracted feature. And all right. So there are some existing methods All right. Okay. So I should say for those existing methods, I want to introduce this to you. Action folder. It is a ICCV 2022 paper. Okay. Why this paper is important? Because it is the first paper used the transformer architecture to predict the start and end time and the class level. So this is the first transformer-based temporal action detection method. Okay. So let me explain. I will spend several slides here to explain the detail. So first, so this is there are several frames of a video. So what it do first is extract the features from those video frames here, and then they use the extracted frame as the input token to a transformer architecture. But they only apply the encoder part of the transformer. Okay. Then they will don't use the decoder part of the of a transformer architecture. And then they will predict the class distribution, the beginning, the end, the start and end time, or the start and end frame of this action. So first, the question is, what is the feature they extract from frames? Okay, so they use this existing video clip representation. It calls two-string. Two-string is okay. First, I need to explain. The two-string idea was proposed in a very important paper. It's called the title is just two-string. Okay, it was published in NIPS 2014. So the idea is this is the idea. So given a video, because video is a temporal sequence of frame, right? So first, you can analyze the single frame like this. How to analyze it, or how to extract the representation of a single frame? Just use a convolutional network. So here you can see the convolution 1, convolution 2, convolution 3, and then finally you will have a representation. Second, because it is a sequence of frames, so you can have the movement between every two consecutive frames. That is called optical flow. For example, this is the first frame and this is the second frame. Then you can, for every pixel in the first frame, it will move to somewhere to the second frame. So this is the flow. So the optical flow means, let me enlarge it. Okay, here, yeah. For every pixel here, you can see there's a movement from the previous frame to the next frame. Okay. Therefore, okay, you can. So what is the image dx here? Is because the movement is two-dimensional, x and y. If you only see the offset on the x-axis, you will get this one. This means the brighter region means the large movement, and the dark region means the shift, small offset. Of course, this is for the y-axis. Okay, so you can use the second path to analyze the movement. So this is the temporal string convolution. So your input will be the dx and dy, and you will not only have a single pair of two images. You will have several optical frames. So what does it mean? For a specific frame, you will analyze its RGB or visual data. You will also analyze its movement data. Okay, so you can extract the representation of this frames or these video clips to get its visual and movement together. So this is called the two-stream. Right? So this is the illustration. For the two-stream, you will use a single image, but several optical flow frames. And through the convolution and fuse them together, then you will have a presentation. But okay. Does Action Former use the two-stream? No. Two-stream is just an idea. Action Former use the I3D representation. So what's the relation between I3D and the two-stream? So here is the for I3D. See this illustration. There is also visual data and optical flow data. The optical flow is the same, but the visual data, they not only use a single frame, they use multiple consecutive frames together. So the I3D, this is also very important paper in the computer vision community. The idea is, okay, suppose here you have a good two-dimensional convolutional neural network to extract the feature for a single frame, right? So what is the I3D? I3D, the I is inflated 3D convolution. So how do you use the idea for multiple frames? Easy. The idea is just apply the good 2D convolutional paper to many consecutive frames together. And for every frame, you will have a representation, right? And apply another convolution, 3D convolution, for each of those frame representation. Okay, then fuse the visual data. But here, visual data, you have information for several frames rather than here, just a single frame. Okay. So you can imagine the I3D representation can carry the richer information than the two-stream representation. Okay, so in this paper, they have two contributions. First is the I3D representation. Second, they also propose a dataset called kinetics. So here, you can see there are the versions of kinetic. Kinetic is 400, 600, 700, and the 700 2020 version. So the number is the number of classes, action classes. And here you can see there are how many clips here. And compare with Tumors 14 and ActivityNet 1.3, kinetic dataset, although it is also a collection of YouTube, but here is the major difference. The format is quite unique. Okay. All of them are around 10 seconds. So, and so the diversity is also better. You know, the Tumors 14 are all sports activity, right? But here you have the human-object interaction, so playing an instrument, or human-human interaction, or shaking hands, or sole body movement, or jumping jacks, etc. So they observe the limitation of the tumors and ActivityNet 1.3 and propose this dataset. But however, the kinetic dataset only works for action classification. It doesn't work for temporal action detection. The reason, what is the reason? The reason is the format, because AV clip, the length of A clip is only 10 seconds only. So let me show you some example. So this is images crops from the kinetics dataset. So you can see this is the robot dancing. So you can see the background is highly diverse. Okay, and however there is you need the goal is to correctly classify which action is in the video. Okay, so let's compare the three data sets. The kinetics, okay, the advantages, it is large enough because there are 600K images, and the number of classes are also the largest, okay. And it also focuses on only for action recognitions. Right? So okay, here, so you can see, the I3D representation and the kinetics dataset are proposed in the same paper. So so you can imagine here, why are they proposed in the same paper? So that is two contributions. One is a huge, modern, effective dataset, and another is a video representation. Why don't they separate the two contributions to two papers? Okay. Yes, yeah. Correct. Yes, correct. Yeah. Okay. So the reason is, if they want to show our I3D representation is the very effective, useful representation, do they need a new dataset to demo it? Yes. They need a new dataset, a large, huge dataset, a very complicated dataset. Why it is complicated? Because there are 400 classes of actions. So they can show on the new challenging 400 classes huge dataset. Our preparation generated the best performance. So this is very convincing, right? So that's the reason they propose two things in a single paper. Okay, so here you can see the table is the table 1 of the action format. So they use I3D as their feature presentation. Okay. So in addition to I3D, there are some other feature presentations. But however, they want to show their paper, the action format, I should say, compare with other methods also using the I3D datasets representations. Their algorithm still works the best. So this is the I3D here. So okay, let me explain here. So there are single stage and two stage. Let me recap it. So single stage means what? What's the difference between single stage and two stages? Yes. Okay. Somehow, but if so, then what is the first stage and what is the second stage? Yes. Yes, correct. So let's see. So let me recap it. So what is the purpose of the action former? What is their goal? Yeah, I should say the input is a video, right? Action recognition. Let me explain. So there are two terms. One is action recognition. Another is temporal action detection. So what's the difference between action recognition and temporal action detection? Somehow, okay. It depends on your input.
The first is just detect the action
Mm-hmm.
and classify them.
Mm-hmm.
And the second one is just maybe detect the action with the start time and the end time.
Yeah, totally correct. So for temporal action detection, you need to detect the start time, the end time, and you also need to classify the action within the within the time period. So this is temporal action detection. And for action recognition, okay, suppose we say action classification is very clear. As action classification means you have, say here, you have 20 classes, and your actions must be one of the 20 classes. Then you need to predict what the class of the action, the given videos, it is. So this is the difference between, and so here, so the action former is a temporal action detection algorithm. So it needs to predict the start and end time of actions, and it also needs to predict the class of that time period. So here the two-stage means what? The two-stage means so you can see there are many methods. For all of them, have the first step to
First segment the time period.
yes.
On the second stage then to predict the classification.
Yes, that's totally correct there. Yeah. And what is the single stage?
Just do those things at the same time.
Totally correct. So that is the first two stage is the single stage. Okay. So what's the I should say what's the advantage of action former? Is first, it is a first single stage. So you can see there are some existing single stage methods, right? But the action former is the first use transformer architecture. First, the single stage method using the transformer architecture. So this is a unique feature. And it shows, using a transformer architecture along with a powerful representation, I3D, okay, they generate the state-of-the-art performance in 2020, in 2022. Yeah, okay. Yes, please.
I have a question just why they are just using like two-stage or single stage. Is it just the training time is different or just why they separate the stage into two stages?
Okay. Because it's very intuitive. Intuitive means if you have a video clip, okay, and so if you can know, there is action, then you can just ignore all other friends. Just pay your attention to this short period and apply a classification algorithm for those friends. Yeah.
I mean, why they just I still don't know why they separate into two stages. Because if single stage can just do both tests, then why they just
Oh, okay. The reason is I should say, it's a history. Because all of the two-stage methods are very old. Okay. Yeah. Right? So when they can do a single stage, why don't they care about the two-stage? So that's the reason. When action format was proposed, all of the two-stage methods are dead. Okay, let's take a break. All right. Okay, based on this question, so here you can see this BNN here, right? Okay. So pay attention to a BN and let's go back to a slide. Okay, here. This is the BNN. So where was it published in ICCV 2019, right? This is 2019 BNN, and let's go back here. So you can see this is ICCV 2019, and then there are a lot of other papers published in 2020, 2021, and 2022, and then in ECCV 2022. Because ECCV is usually held in October, so this is almost the end of the 2022 year. So they proposed the action format. So that's the reason why Dina asked, if you can predict both action start and time and the action class together, why do you need the two stages? Because they are all the papers, all the methods. Okay. All right. Yes.
As an author, how do you choose which previous models to include in your results tables?
Okay, usually this is, for example, you see the BGN, the DBG, when they submitted their paper, they will include the BNN because their performance is better than this. Okay, and then when the PGCN, when they submit the paper, they will include the BNN and the DBG because their performance is better than the previous two methods. Then so here, when action format want to submit a paper, they will compare some existing paper, and the paper will include all the existing papers.
But like, why so many versus because they've already shown that their model is better, right? Mm-hmm. So why not include just the most recent few models which are better?
Some of the authors did it.
Sorry, some of the authors.
Some of authors will only include the recently published 2 or 3 papers.
But some authors like to put in all of them.
That's right.
And then, but they would not have run these results.
No.
Themselves.
Usually they have no, because there are too many papers. They just copy those numbers.
Yeah.
Okay.
Because this is an existing data set, right? It's not their data set.
No. Some authors didn't release their code.
Yeah.
And it is very difficult to reproduce their experimental results. So most of us just copy those numbers in their papers. Okay, so my next question is, so now you see stimulus 14 and activity point 1, net 1.3 are 2 data sets. What are the numbers? 0.3, 0.4, and etc. here. What are those numbers? And suppose you see so of course this is the average. What does the average mean? And see there is a number 82.1. What does it mean? First, what is 0.3 mean?
I guess it's more like overlap.
Yes, correct. Overlap. Yeah. Okay, so let's explain what it is. So how to measure the performance? It's the same as the object detection. So yes, the 0.3 is the for object detection, you will have the IOU, intersection over union. But this is the temporal action detection. So that is a TIOU, temporal, right? Okay. And so for given a threshold for the TIOU, you will calculate the mean average precision. Okay, so this is given the threshold, you will calculate the mean average precision. And I will explain how to calculate the mean average precision later. And when you have several thresholds from 0.3, and then you can calculate the mean average precision for each threshold, and so you will get the average. The average is just the average of the 5 numbers here, right? Okay, so that's what. So what is IOU and TIOU? So let's go back to the object detection. So object detection means if you have a ground truth stable, this is the yellow frames, yellow blocks here, and you have a predicted region. So this is the dashed block here. Okay, then you will have an intersection of the two regions. So this is the orange region, and you will also have the union. So union is this part. Okay, then you can calculate their ratio. Yeah. So here this, and this is just for their area. You will also have confidence. This means if you predict this is a kite, then how about your confidence? So this confidence is 0.6. So this image is cropped from our reference book, the computer vision and application. And then when you, so let me explain another term. It means, so for precision, the definition is what? The true positive plus true false positive divide true positive. So this is just the mathematical definition. And then this is also this is precision, and this is a recall, right? Okay. And what is the mean average precision? So okay, here, let me show you an example. So suppose this is the ground truth. So there are 4 classes: trunk, dog, person, and teddy. Okay, and suppose this is your detected result. Then, how do you calculate the mean average precision for the class of dog? So here is you will first show list all of the regions your algorithm detect it as a dog. So let's here. So there are 1, 2, 3, 4, 5, 6, 7 regions you detect as dog. But okay, you have a threshold of the IOU, right? So you can calculate whether it satisfies the threshold. If the IOU value is greater than the IOU threshold, then it will be a true positive. The positive means you assume that those regions are all dogs, so they are all of them are positive. But some of them are true positive, some of them are false positive. What is the false positive for the example? Because the IOU is less than the threshold, you only detect this region, so it will treat it as a false. It's not a real dog, so this is false positive. And here again, because this region, it covers the dog's head, but compared with the ground truth regions, the overlapping is too small, so it is also a false positive, right? Along their confidence scores. Okay. Then, okay, you can create a table, sort them by the confidence score. So here, and this is the matrix table: true positive or false positive. Okay, then you can calculate the cumulative positive. So for the first row, it is 1 because this is true positive, and also the cumulative false positive. So this is 0. Okay, then you can calculate your precision and recall here. Here, the precision follows the same definition as here. It means the true positive plus false positive and divided by the true positive. So this is 1 divided by 1 plus 0 is 1. until the second row, you have a 1 truth positive and a 1 false positive. So the precision is 1 divided 1 plus 1. So it is 0.5. And then you can you can fill in all of the cells in this column. But however, the recall, the definition of recall is cumulative true positive divided by total ground truth. So what is the total ground truth? It means how many blocks you have in your ground truth. So here you have 1 truck, 2 person, 1 teddy, and 13 or 12 dogs blocks here. So the total ground truth is 16. And then you can calculate the recall value here. Okay, so you have 7 instances. So you will have 7 precision and 7 recall. Then this is a 1, 2, 3, 4, 5, 6, 7 points on the precision recall plan. And then you extend the first point to the left and the last point to the right. Then you will have a region under the zigzag curve. So the region, because the range of the precision is 0 to 1. So this is 0 to 1 for the vertical axis, and 0 to 1 to the horizontal vertices. So the highlighted region, the area of the highlighted region is the average precision. So that is average precision for dog only. Okay, for dog only. So you can and we also need to calculate the average precision for trunk, for person, and for the teddy classes. Okay, so you will have 4 average precision, right? And the mean of the 4 average precision is the mean average precision. Okay, so this is the value of the mean average precision. So what is the 82.1? In fact, this is 82.1%. Okay. Yes?
How come the recall is calculated across class, even though it's done for every class? So the recall calculation is divided by 16, which
Right.
is the count from every class.
Yes.
But the maximum value is 12, or in the case of truck, is 1.
Mm-hmm.
Why isn't it per class, like 12 out of 12?
Do you mean here? Okay, for the trunk, the number 16 is also fixed.
Yeah.
Mm-hmm.
Why?
Why? I don't know. I don't know why it is this. Okay. However, here. So let's see this case. For trunk, if the positive is so you will see a lot of values here, right? Okay. And if they are and for trunk, suppose there is a single positive region.
Yeah.
Then and the recall value is fixed. Then you will have just a single point.
Yeah.
And when you extend the point horizontally, if if it is a true positive, then the highlighted region will still be very large.
But if the recall will be 0.08, right? So it'll be, yeah, it'll be 0.08 recall, and then the precision will either be 0 or 1, I guess.
So the recall is 0. So suppose it's 0.8.
Yeah.
Okay, what does this mean? Here, this is a recall.
Yeah.
It is 0.8. It means somewhere here.
Yeah.
Okay, then suppose its precision is high. Then no matter how large the recall is. I think I can draw something here.
Yeah.
Okay, Suppose the recoil is 0.0 high like this. If you have just a point and this position is high, then when you draw the region like this one, yeah.
Becomes either 1 or 0.
Mm-hmm. No. It's become almost a 1.
Sorry, but I mean, if you predict incorrectly, then you would be 0.
Yes.
Your precision would be 0.
That's right.
Yeah.
Mm.
But it seems like the class metric is heavily affected by the number of samples in the class,
Mm-hmm.
which is surprising.
Mm-hmm. Okay. Yes, please.
This PR curve is for different classes or
A single class. So this PR curve is only for the dog class. Let me explain here. There are 4 classes: dog, trunk, person, and TAD. Okay, and we only calculate the average precision for dog. So this is an example for dog only. Okay, yeah. So if you also need to calculate this PR curve for the other 3 classes. Okay, then for every class you will have an average precision, and you calculate the average of the 4 classes, you will get the mean average precision.
I mean because if one class is, then if we call it the precision should be one number separate.
What do you mean one number separate?
It's like for all class,
Mm-hmm.
and its recall is like a number, and its precision is like a number.
Oh, okay, no. Yeah, that's right. For dog, so here we have 7 positive, right? Yeah, it means, so this is our detected result. We have 1, 2, 3, 4, 5, 7 regions. The algorithm think they are dogs. Okay, so we have 7 positive results. But some of them are true positive. Some of them are false positive. Okay, so for this and this is false positive and this is false positive because their IOU is less than the threshold. Okay, right? When you have 7 positive and sorted by the conference scores, you will have 7 rows. Yeah, when you have 7 rows, you will have the cumulative positive and the cumulative negative, false positive. Okay.
It's different from the normal PR.
Right, normal PR curve. Yeah. Okay, yeah. So, okay, you can calculate the mean of every. So, what we talk about is for object detection on an image. Here, we can apply it to temporal domain, the same. The idea is automated. For example, this is time, and you have several ground truths classes or actions, and this is your predicted result. Now, you consider one class only, just like we consider dog only. Okay. Here, let's suppose we only consider the pole vault. Okay. So let's remove all of them. So this is the pole vault. Let's ignore the diving and the high jump. And we also calculate those positive. So this is first, second, third, and fourth. Okay, then we apply the temporal IOU. Suppose that this is threshold. Then this will become the true positive, and the 2 will become the false positive because their IOU is less than the threshold. So that's it. For temporal action detection, we use totally the same metric or the same mechanic to calculate their performance. So here now you can understand. So how do we calculate those numbers? How do we generate those numbers? Okay. All right. Okay. Now we know the metric. Now we can start its design. Okay. So first, given video, it will use the I3D representation to extract the feature for AB frame. I should not say everything, because when you extract the I3D representation, you in fact look several threads together. And however, for every time step, you will have a single representation for several threads nearby. Okay. Then, when you have the representation, you will apply a transformer encoder. So this is a transformer encoder. Then, after several layers, what will you generate? A latent distribution, right? Okay, for the transformer. And for the typical transformer, you will have a decoder. Then your decoder will translate your latent representation to your final representation. And here in the action format, no, they don't have the decoder. They only use the encoder part to get the latent representation. And then they use two simple convolutional network to predict the start time, the end time, and so there are two heads. One head to predict the time, another head to predict the class probability distribution. Okay. Then pay attention here. You can see this is a downsample, right? In typical transformer architecture, there is no such downsample. Let me show you. Yeah, okay, so this is the typical transformer architecture. No downsample. So they add a new operation, downsample here. Why do they need to create it? This is their design. Okay. Why do they need this downsample? Because they want to create a feature pyramid. So let me explain. So there are several layers of their architecture transformer block, right? So let me explain. There are totally 7 layers of the transformer architecture. For the first two blocks, they doesn't use the downsample block. And for the following, the third, the fourth, they will apply the downsample. So then this is the result. For the they will generate for the first output of the block. They call it as Z1, and it is generated by the second transformer block. The length means the number of threads or the number of representations is the same as the input. And then for the third transformer architecture, they start to downsample it. When they downsample, what will happen? The length of the number will be only half of the original one. And they call it Z2. And then when they apply all the 7 transformer blocks, the lattice layer, they will generate only 30 seconds length. So visualize it is something like this. Suppose this is the input, and then for the Z1, there were a lot of Z2, they were less, and Z3, Z4, and so you see. Okay, so it looks like a pyramid. So then, they will, once they create the pyramid, then they will apply the convolutional based boundary head and the classification head on each of the 7 layers. Okay, so this is the idea. So what do they predict? So here you see there is a peak. So what does the peak mean? The peak. This is the starting time. It may generate by the first layer, or this may generate by Z1, or Z2 or reset. It's up to them. Any of them are possible. Okay, and through the 7 layers, they will sum them up and create this peak. Okay. Some weighted average by what? By the confidence score. So they will generate something like this. And this is their classification distribution. Okay, so they will predict that from here to here, there is a high jump actually. Right? Okay, sorry. This is the 41st page. But I need to stop here. I have total, how many pages do I have? No, I think 70 or something. Okay, 69. But I need to stop here, sorry. Okay, if you still have a remaining time, I will keep going on. But I think now I need to take it. And now it's I cannot use all of your time.